specific psi, the second order nonlinear system, then we have n independent optical parametric oscillator pulses, which is sequentially detected its amplitude and the phase by an overnight detector. And based on the mechanism result, we can compute the coupling in this electronic circuit, and based on that information, we can modulate amplitude and phase of the feedback pulse, which is taken from the pump laser and injected back to any sort of a pulse. In this way, we can actually decrease the number of oscillators from n to 1 and the number of connections from n squared to 1. So that's relatively simple to implement this sort. The first implementation of this idea was done at Stanford University, and this is the experimental setup. The first coherent Ising machine. The ring cavity consists of 4 layers, free space ring cavity. Round trip time is 16 nanoseconds. The first modulus laser, fiber modulus laser, has a repetition period of 4 nanoseconds, so we can generate 4 independent OPO pulses. And in this case, we implement 3 optical delay lines. Delay line 1 with 1 bit delay time introduces clockwise Bialek-Neighbor coupling. Delay line 2, 2 bit delay introduces diagonal coupling. And finally, the delay line 3 with 3 bit delay introduces counterclockwise Bialek-Neighbor coupling. In this way, complete graph can be implemented. Computational result can be detected by the simple differential phase detector, and this is a measurement result. When we implement LP-Hart Ising program with n equal 4, success probability to find ground state is larger than 99.9%, which means that we run the system 1,000 times, never fail. So success probability is 39. We recently, the NII people extended this sort of machine to n equals 16 by replacing clock frequency of the pump laser from 250 MHz to 1 GHz. And again, for n equals 16, 1,000 run, no failure. So the success probability is 99.9% or higher. If we use brute force search, the success probability, the last success probability is 38% and 0.01%. So there's some improvement experimentally confirmed. NTP people actually implemented their large-scale system in their fiber-based ring cavity. Now the cavity is a 1 kilometer optical fiber, and the clock frequency, moderate frequency of the pump laser is now 2 GHz, so that approximately 10,000 independent OPO machines are actually running, and those pulses are actually detected by Homodyne detector. And this is a Homodyne detector which without mutual coupling at the critical point, the system picks up either 0 phase or pi phase randomly, and the histogram really shows 50% random choice for this oscillation phase. And right panel shows the dynamical behavior. And this is an round trip 100. We actually switch on the pump laser. Then our system actually starts from vacuum state and from the squeezed vacuum state or anti-squeezed vacuum state, and then bypass it into either 0 phase or pi phase. And from here to here, it is about 80 round trips. That is our computational time to get the desired result. Now, how good this machine should be? We actually performed a benchmark study using the numerical simulation. The program is called MaxCut. This is our famous Petersen graph with n equals 10 vertices. Each vertex has 3 edges, so it's a cubic graph. We are asked to cut this sort of graph into 2 subsets in order to maximize the range of the cut. And this program, I will skip the detailed explanation. If we replace the wedge A by the negative Ising coupling constant, the ground state which minimizes the Ising energy, Ising Hamilton, is incidentally the solution for maximizing the cut to the given graph. So it is basically a very suitable target for benchmark study. This is our benchmark study result. If we increase the number of vertices from n equals 4 to n equals 20, the number of possible graph increases also 1 to 510,000. We have to solve all of them because we don't know a priori which particular graph is hard. And most of the graphs out of 510 graphs are easy, and only 5 or 6 graphs are really hard. And this table shows the success probability to find the ground state for all those sort of graphs. And as you can see that with increasing the graph size, the success probability monotonically decreases, which is a bad sign. But if the network is actually biased at the critical point of OPO phase transition, not at well above threshold, the system enjoys almost a constant success probability here, at least up to n equals 20. This number can be compared to the success probability of 10 to the minus 6 for brute force search. So this is the distinct advantage of this approach. If we go to a much larger graph, the ground state we cannot compute because it takes too long. So we can actually use our semi-definite program, this is actually the popular algorithm, which has 97.8% accuracy guarantee and widely used in modern computer science. And if we solve n equals 800, n equals 4,000 completely, And with the same approximation accuracy by simulating the annealing coherentizing machine, the result is shown here. And the computational time as a function of program size is summarized here. STP actually scales program size n to the power of 3.5, and the simulated annealing scales n squared. And for the program size of n equal to 20,000, which is relatively small for computer scientists, it takes 20 days and 100 seconds. If we believe this scaling and scale to 100,000 problem, which is still a small problem for practical application, it takes 5 years and 1 hour. Coherentizing machine, as I said, it is basically Canon delay time on OPM network. We switch on the pump and wait for the steady state is reached. And this is approximately 1 millisecond and independent of the program size. Let me switch that here and talk about homomorphic encryption. This is a very brief summary of cryptography, and it is said in the text. 700 BC, the first crypto system called Scutari appeared in Spartan, introduced by Spartans, and then 50 BC, Caesar ciphers used by Roman Empire, and then famous Enigma by German military. For the last 2,700 years, the cryptography has been simply a technique for protecting the information in communication channels. And this is because most of the application area is actually the military, or at most diplomacy. But around 1970, the internet came along, and everyone would like to communicate without sharing the secret key anymore. So 7 years later, the famous RSA was invented, and now everyone can use public key to encode, but only one person can encode with private key. So the really important evolution happened in 1977. But then the second wave came around 2000. Around 2000, the cloud computer came along, and everyone would like to store the precious data in public domain server, and they would like to use this server as a computing machine too. Then the cyber attack becomes a serious problem. And then gently came in 2009, introduced the fully homomorphic encryption, which can allow the secure storage and secure computation simultaneously in public servers. So now it is becoming a secure platform for information storage and processing in public servers. Different users can store information securely, compute the secrets, and decrypt computational results. Such a future is going to be coming soon, but the reality is actually the fully homomorphic encryption still costs very, very expensive. 1 bit in plain text costs, say, 800 bit public key. So it's awfully expensive. We are interested in the encryption method based on unitary matrix. What coherent Eigen machine does after all, it is basically solve this eigenvalue problem with the Eigen-Hamiltonian. And if we simply multiply arbitrary unitary matrix from the left, the resulting equation tells us that the new Hamiltonian UHU minus 1 has a new energy eigenstate U over phi, and phi n is the eigenenergy state, eigenstate of the original Hamiltonian with identical eigenenergy. So the Hamiltonian changed, the ground state or eigenstate changed, but the eigenenergy spectrum is preserved. So we can decode our computational result if you know the matrix U. And that's basically the decryption. What kind of a unitary matrix can be used? That's an open question. If we introduce bit flip, there is some program. If we add permutation, there is some program still there. And how about embedding random graph? We are currently exploring all those different possibilities. But the final system we would like to establish someday is summarized in this slide. Suppose the user would like to store the precious plain text in server. He can actually encrypt by his own unitary matrix, and then the coherent Eigen machine actually compute on this a new Hamiltonian and return this encrypted state. The server manager never knows what the file is because he doesn't know the unitary matrix. Now, this communication is clearly classical because information which is transmitted from user to the server manager is basically the real number Jij matrix. If the third-party client would like to get only the computational result, the user actually issued two different unitary matrix, and the secondary encryption and the client decryption and so on. And in this scenario, server manager and the client cannot access the program data Jij, but the only client can only know the final computational result. This is the last slide I would like to summarize my talk. Last autumn, the Japanese government launched the new national project called IMPACT, and we would like to establish the brain-like computing network. It is well known that in human brains, the optimum neural network is formed each time, depending on specific missions. This is again function of fMRI data. And what is our dream? Our dream is basically such a network type computing machine. Our central computer is a general server, standard server. It accepts input and compute and provide output if the task is not too hard. But if the task is combinatorial optimization, then the task goes to our coherent Eigen machine. If the task is a secure storage or computation, it should go to homomorphic Ising machine, as I explained tonight. I didn't talk about the another two new machines. There is another similar machine called coherent XY machine, which is good for cognitive detection, modularity, or associative memory, or coherent Heisenberg machine, which is good for quantum simulation. And with that, I should stop here. Thank you very much.
Okay, so now it's time to open the envelope. Now I don't have it in an envelope, but I've written it down on a piece of paper. So it's one, yes. So we have one best poster award and one best student paper award. Okay, and the best poster award goes to Mark Kaplan. And the award for the best student paper goes to Alexandru Georgiou. Okay, so I'll be talking about long-range QKD with time and frequency. First with frequency, and then with hybrid time and frequency, and how that improves rates in broadband solid-state memories like the ones we heard about in the tutorial in the morning using AFCs. Yeah. Okay, so the contents were there for a slightly longer talk, but let me just tell you how it structures this. First, I'll explain the repeater architecture that we're analyzing, but our analysis in principle can be applied to other kinds of architectures, which especially use, don't use quantum logic in the sense that if it's only linear optics, then it can in principle be applied to that as well. So basically, after describing that, what we do is do an exact analysis and find a quantum state after a certain number of entangled swaps. So you have the exact quantum state, which includes all the losses and the detectors and channel losses and dark and all kinds of stuff. But I'll tell you what assumptions we make. And then using that state, you can do any number of things. And one of the things we do is find secret key rates and check performance of those as we vary the parameters. So with dark the detectors, and we plot the rates. And then the next we do is numerical simulations with source imperfections. That's something that we don't include in the analytic calculations. With source imperfections, and if I have time, I'll talk a little bit about our current work on using time modes to improve the rate envelope. Okay, so the repeater architecture is basically something that looks like this. So you have what's called an elementary link, the shaded region here, and you have quantum memories. So you have a certain distance, and you put quantum memories in there, and then in between two quantum memories or quantum memory and the end is what we call an elementary link. And in the middle of an elementary link is a Bell state measurement. There's a linear optic Bell state measurement which has a success probability of half if everything's perfect. So, and you have entanglement sources over here where one half of it goes into the quantum memory and the other half goes to the center of the elementary link. Similarly, of this quantum memory, there's one half that goes into the memory and one half that goes here. And these two halves that you get is a Bell state measurement that's performed, and you get an entangled pair across these two memories. But as discussed in the morning, in fact, this frequency multiplexing is possible because this Bell state measurement has only success probability of half. We can boost the success probability using the frequency multiplexing. So what happens is this state, the entangled pairs are created in many frequency channels, and half of those goes into the quantum memory, and the other half goes to the Bell state measurement. And if you have a lot of frequency channels like this, the success in one of them will happen with high probability, and that frequency, the successful frequency information, is sent back to both the quantum memories. Okay, so then similarly, say F1 works over here, and some F2 works over here. This quantum memory has that, and this quantum memory has F1, and now these two quantum memories translate that frequency to a standard frequency, and they're now matched, and you can generate an entangled pair across the whole thing, and that's how this architecture works. So we basically analyze, what happens when you have this kind of thing where, this channel has losses, this quantum memory has, some inefficiency, and all the detectors are single photon detectors, but they can have dark links and inefficiencies. The only thing we assume is that the state is perfectly entangled. Excuse me, that there are no two photon terms. In dual wave basis, this is what state looks like. And we also don't consider some other things like mode mismatch, which in principle can be done, but we don't do it in this analysis here. Okay, so more importantly, there's no purification done in this architecture, and so we don't have that. But still, as I will show you, it beats the repeaterless upper bound, called the TGW bound, even in spite of this, but the envelope is exponentially bad, as in it scales exponentially. But when you use time modes, it turns out that it can be sub-exponential, and I'll talk a little bit about that. Okay, so these are just the parameters that we use that I mentioned just now. Okay, so so what do we do exactly? So you have the elementary link, and when you do the Bell state measurement and it's successful, you have an entangled pair across the elementary link. Now you take two such pairs and then do a Bell swap, and you get another one. And you take two such pairs and then Bell swap. So you go in steps of two powers of two like that. And at each level, with the state that we call is rho I, And that's essentially what we find exactly. So basically, if you take m plus as your initial state, it turns out that after any number of bell swaps, which, and the detectors, we have inefficiencies and dark clicks and everything, it still turns out that the final state is in the span of the psi 0, psi 1, psi 2, psi 3. Of course, there can be cross terms and everything, but it turns out that it's not an arbitrary state in this, but it turns out to be something that looks like this. Of course, we don't have to write it like this, but it turns out to be better if we pull out the m plus and m minus terms separately and the classical correlation separately. So AI, BI, CIDIs are coefficients that you get at the ith level, and because now if you take two such rho i's and you want to find rho I plus 1, you get some coefficients AI plus 1, BI plus 1, and so on, which can be calculated in terms of AI, BI, CIDI. That's not so hard to do. Once you have that, the point is now that we actually want not in terms of the previous step, but all the way back to the beginning. So we actually want AI, BI, CIDIs in terms of the initial ones, initial AI, BI, A1, B1, C1, and D1. And such iterative maps, when you're given the coefficients at a certain level, you can find the next level. But then you can iterate like this, but then to go back to the initial stage is not so easy, and such iterative maps, in fact, show some strange behavior, like chaotic behavior. And this one's no exception, although we're not in the chaotic regime with those parameters. But it turns out that the map that's relevant to this is something called the logistic map. It's called the logistic map because it looks like this. This is actually the variant of the logistic map that we had to solve, but the logistic map itself is just Wi plus 1 is Wi times 1 minus Wi with some coefficient. It's called the logistic map because if you think of Wi as a bit, 1 minus Wi is it's not, and this looks like an and. It's not exactly that because Wi lies between 0 and 1, and it's not exactly 0 or 1. Now, if we assume that there are no dark clicks in any of the detectors, it turns out that we get exactly the logistic map, and we could use a solution of that to find out. But when we introduce dark clicks, we get this variant of the logistic map, which we were able to solve by modifying the ansatz, by putting in a parameter and solving for that parameter, and then we were able to solve this particular one and get AI, BI, CIs, and DIs in terms of the initial A's and of course I. So this is what the solution looks like. This is, we won't tell you much, but then we were able to use these, coefficients, of course, to find the exact state, and then plot the state in terms of, so we find the secret key rate using this formula, and then plot that. So secret key rate ends up being, of course, in terms of the parameters of your detectors, the losses in your channel, and your memory loss. So once we find that, we can find the secret key rate and also the quantum bit error rate. So for example, if you do I swaps, and at that point if you measure, you have that swap over there, and they find out what the quantum bit error rate is, assuming they measure on the same basis, then you get QI. And then suppose you do the next level swap, and then if you do find the quantum bit error rate, that's QI plus 1, and they turn out to be related by this quantity, in this fashion. So you can find several things. We can also find the fidelity of the final state with some state that you hope to get. So it turns out that when you plot this, you get curves that look like, like this, which have three kind of different regimes. So these curves with different colors are for different number of repeaters. Where here we're going in powers of 2, so the number of, actually n is the number of elementary links, the number of repeaters is 1 less than that. But in terms of the number of elementary links, you have 1, 2, 4, 8, 16, 32. And as you can see, this is the envelope, and this is what we want to focus on. For example, if you want to go up to 2000, you wouldn't use 4. You would have to look at the envelope and then use the right number of repeaters at that point. So each curve turns out to have three different, parts. There's this low loss flat part. And this is because we don't use multiple successes in the multiplexing. When you use multiple successes efficiently, then you get a slight improvement in this flat part. I'll tell you about later. And this is the part that's due to the channel loss, which is exponential. And it makes the curve fall exponentially with distance. And this is the part that's due to dark clicks. When the voltage resistance comes to a certain point, the dark clicks take over, and you get a cliff. So we could find out how dark clicks affect this rate loss envelope. One other thing that's kind of useful to find is Lmax, which is basically where this dark cliff occurs. So if you fix the number of repeaters, what is the maximum length you can go up to with these repeaters where you hit this cliff? And that's given by this formula, which is in terms of the parameters, in terms of detectors and losses and stuff. So as you keep increasing dark clicks, as you can see, dark click rates, as you can see, the cliffs start appearing closer and closer earlier, but the envelope doesn't change. It's still the same. But of course, if you increase it by a lot, even though the envelope doesn't change, there's no curve over here. So you have to go down to a large number of repeaters, and your initial rate itself will be very low. So there's not much point doing that. So dark clicks affect the cliffs, but then not the envelope, but up to a certain point. Okay, so this is what we did analytically. Then we started doing numerical simulations to find out how 2-photon or multi-photon errors affect the rates. So the state that we consider is something that's a truncated SPDC, two-mode SPDC state that looks like this. With the probability P1, you have the right state. With probability P2, you have the 2-photon term state. And 1 minus P1, P2 is the value. So we fixed P1 to be 0.9 and then started varying P2. And as P2 increases, we found, somewhat surprisingly, that it's really, really detrimental. In fact, if you have P2 be really, really small, this is nowhere near the SPDC kind of thing where P2 is square of P1. So even P2 is extremely small. It turns out that, little n here is log of capital N. So this n equal to 3 is 8 elementary links, that's 7 repeaters. It turns out that 7 repeater curve crashes in the sense that it's below this, it's completely inside these other ones. In other words, at no distance at all, at any point in going to 8 repeaters, you never have to do that because you never get any improvement. So if you increase P2 even more, at some point n equal to 2 crashes, so there's no point going up to 4 repeaters, you never get any improvement. And finally, if you keep increasing it even more, even n equal to 1 crashes. So finally you're left with n equal to 0, that's 1 elementary link and no repeaters. So eventually, having no repeaters with this much P2 is what you have to do. Okay, and then this, let me skip over this. This is the part where we try to incorporate the P2 effect analytically to get the exact calculation done for P2, and we found some interesting connections, but I want to move to the next part, where suppose we do want to use SPDCs, then what can we do in this architecture to get back the rates that we had, or at least slightly better than the one we saw just now? So for that, we noticed that actually, so if you use SPD, single photon detectors, then as we saw before, even with small amount of P2, no